This is part 11 of the Module 9 lecture. In this part, I'm going to introduce the comparison of the proportions of two independent populations. Again, this topic is discussed in your textbook in section 10.5. All right, looking at this diagram that I have been using to guide the discussion in this module, you can see that we look at the comparison of independent populations, and we look at the continuous random variable where we compare the variances, the means with unequal variances, and the means with equal variances. Also, for a continuous random variable, we talked about the case of dependent samples. So now we're going to talk about the last topic, which is a comparison of two independent populations, but now we want to talk about comparing the proportions. So in this case, we're dealing with a discrete random variable. So this is our last topic in this module. And here's an interesting example. So a medical research team conducted a study to test the effect of a cholesterol reducing medication. So at the end of the study, the researchers found that of the 4,700 randomly selected subjects who took the medication, 301 of them died of heart disease. And of the 4,300 randomly selected subjects who took a placebo, 357 died of the heart disease. So in here, the significance level of 0.01, the researchers want to see if they can conclude that the death rate, the proportion of people that die due to heart disease, is lower for those who took the medication, we're going to call that proportion P sub m, than those who took the placebo, we're going to call that P sub PL. And also they want us to calculate a 99% confidence interval. And of course, interpret the results that we obtain. And this is a very pertinent example because this is sort of the trials that are performed when a new drug or a new vaccine is being tested. All right. Again, you may be tired of me showing you this diagram, but I want to emphasize that it's very important to follow the 5 steps when you're performing a hypothesis test, because that will guide you and ensure that you complete all the steps. All right, so when we're comparing two proportions, our objective is to test the hypothesis about two independent population proportions, pi 1 and pi 2. And we're going to use the sample proportions p sub 1 and p sub 2 to make an inference about these two population proportions. And we're going to do the same thing we did for comparing the means from two independent populations. We're going to use the difference of the sample estimates to make an inference about the difference of the population parameters. In this case, we're going to use the difference of the two proportions to make an inference about the difference of the two population proportions. And as before, testing the hypothesis about the difference of the two proportions, we need to rely on the sampling distribution of the difference of the sample proportions. So the question is, well, what is the sampling distribution for the difference of these two proportions? Well, as long as we have a sufficiently large sample size, and these samples come from binomial experiments, and by large sample size, I mean that the number of trials in the first experiment times the probability of success of the first experiment, or the estimate of the proportion, I should say, should be at least 5. And again, the number of observations times 1 minus the sample proportion of success should be at least 5. The same for the second sample. The sample size of the second sample times the proportion of success for the second sample should be at least 5. And the second sample size times 1 minus the proportion of success, that should also be 5. So now, before we always had 2 verifications, these 2, and now because we have 2 samples, we need to do it for the second sample as well. So if these samples come from independent binomial experiment and the sample sizes are large, demonstrated by performing these calculations, then the sampling distribution of P1 minus P2 is approximated with a normal distribution with an estimated mean of the difference of the 2 proportions. And why estimated mean? Well, because we don't know the actual values of the population proportions. So we rely on the calculated values of the sample proportions. Similarly, the standard error of the sampling distribution of the difference of the proportions is estimated by using the sample proportions as shown here. All right, now under the null hypothesis, we have the equal sign. Under the null hypothesis, the first population proportion is equal to the second proportion. So we can say that they are, we have a single common proportion, pi. And because when you obtain 2 samples, you obtain 2 sample proportions. And so you P1 and P2, but they are estimating the same population proportion. So we do what we did before when we have equal variances. We combine them into a single estimate, and we call it the pool estimate of the proportion. And we calculate it in this way. So if you know the sample size and the proportions, then you use this formula to calculate that. If in the problem you're given the number of successes in the first sample and the number of successes in the second sample and the number of trials in the first sample and the number of trials in the second sample, then you can calculate this pool estimate of the single proportion and this using this part of the equation. This table just shows you what each of these symbols represents. All right, so once that you have this estimate of the pool proportion, the pool sample proportion, I should say, then you can construct the test statistic, which comes from the sampling distribution of the difference of proportions. And so we have the difference of proportions that comes from the sample and the difference of population proportions that come from the null hypothesis. That's why I have this sub-zero here. And then to calculate the standard error in or the denominator of the test statistic, we use the pool estimate of the proportion times the inverse of the sample sizes. So that's how we're going to calculate the test statistic. And then because we're comparing 2 proportions, then we're going to do it in the same way that we did the comparison. Oh, I should say comparing 2 proportions for 2 independent populations. So we're going to use the difference of the proportions to make an inference. So if you have a 2-tailed test, we said that the difference of the first proportion minus the second proportion is equal to 0, or that difference is different from 0 in the case of a 2-tailed test. And as before, here I'm using 0, but when you look at the problem from the context of the problem, that difference might not be 0. So please pay attention to what the problem is telling you. Now, if you have a tail test, the left tail test, then you're looking at the difference of the 2 proportions being less than 0 under the null hypothesis and being equal or larger than 0 under the null hypothesis. If you're looking at right tail test, then the difference of the proportions will be bigger than 0 under the alternative hypothesis, or less or equal than 0 under the null hypothesis. So this is the same idea when we compare the means of 2 independent populations. All right, so if you use the critical value approach to test the null hypothesis, well, we're going to use the same technique or the same approach that we learned in Module 9. So if you have a left tail test, well, your rejection region is on the left side. And you're going to use now table 4 with the significance level, and you're going to look for a z-value that is negative. That will define the lower rejection region. If you have a right tail test, now you're looking for a z-value on the right side of the distribution will be positive, and that will define the rejection region on the right side of the distribution. If you're working, if you have a 2-tailed test, then you need to find the z-critical for the lower tail and the z-critical for the upper tail. and we use alpha over 2 to find that. So in that way, we define the rejection regions. All right, if you decide to use the p-value approach, again, the decision to reject the null hypothesis is if the p-value is less than alpha, we reject the null hypothesis. If the p-value is larger than alpha, we do not reject the null hypothesis. And then to find the p-values is exactly the same thing that we've done. We did it in Module 9, where if you have a left tail test, the p-value is the probability to the left of the observed value of the test statistic. If you have a right tail test, then the p-value is the probability to the right of the z observed. And if you have a two-tailed test, well, depends. If the z value, if the value of the test statistic is less than 0, it is negative, then you do the p-value is 2 times the probability to the left of that value. If the z value is positive, then the p-value is 2 times the 1 minus the probability to the left of the z observed. So again, the same rule that we learned in Module 9. All right, and going back all the way to Module 8, then the confidence interval for the difference is now defined as this. So now we have the difference of the two sample proportions minus z alpha over 2, which is obtained from table 4 with alpha divided by 2. And we use the first proportion times the probability of 1 minus the first proportion divided by the first sample size. And then plus the second proportion minus 1 minus the second proportion, that divided by the second sample size. So this is the margin of error. And so you subtract that from the difference to find the lower confidence interval. And then you add the margin of error to this difference to find the upper confidence interval limit. Now, notice that because under the confidence interval calculation, we don't make any assumptions about the population proportions. So we cannot say that they are equal, and therefore we do not pool the two sample proportions into a single pool estimate. So please be careful. There is a difference between these formulas. Okay, so when we're using the confidence interval equation, we do not pool the proportions into a single estimate, as we do if we are testing a hypothesis and calculating the test statistic. So be careful with making that distinction so that you don't make a mistake when you're calculating the confidence intervals. All right, I'm going to stop here. In the next segment, we're going to review this example and see how we perform a comparison of proportions from two independent populations.